Okay, so you remember how in our example we had those two cups, right? And this is not a very good representation, I suppose. And we had, actually, it's one of my daughter's bendy straw, and that's a really horrible tasting food coloring, so I hope she doesn't mind. She's asleep. Anyways, and I put the liquid in, right, on these two. And what always happened is the liquid levels on both sides reached the same level. And regardless of where I moved one of the cups, the goal of the liquid was always to reach that same level. Now, it turns out chemistry has a way of measuring that for chemical reactions, and we call that the equilibrium constant. So we're going to call that K. Now, K will often have other subscripts written with it, but as it turns out, right, they're all written the same way. So I'm going to show you how to write some of these and their form. And one of the things I expect you to be able to do is if I give you sort of a random chemical reaction, you should be able to write the equilibrium constant expression for that. That simply means write the equation for the equilibrium constant. So K, right, is my equilibrium constant. In general, it's products over reactants. Now, let's say the reaction is this. This is the simplest case scenario. And we use an equilibrium arrow because you know how I can make the liquid go backwards and forwards? It really, even when it's sitting at a level, the liquid in that tube is traveling in both directions at all times. And if you have the time to do this, and you've got a nice glass tube or something, or a straw, and you put food coloring into one side, and you make the levels the same, and you leave it for a week, eventually the liquid, some of it will flow from one side to the other, and you'll see the food coloring on the other side. Okay, so if we have A in equilibrium with B, so this is my equilibrium arrow. The equilibrium constant is going to be written like this. K is equal to, and I'm going to show you this new symbol, these brackets, B over A. And this bracket represents a new unit. And you don't need to do anything with it. I just want you to know what it is. You'll learn like how to deal with this unit later. But it simply means this. This bracket means moles in a liter. It's the concentration. So if I had 1 molar A, that's the term we use, and put what that would mean is in every liter there's 1 mole of A. If it's 2 molar A, then it's 2 moles of A in every liter. So it's just a concentration, okay? Those numbers will be given for it to you, or you'll calculate them, but you won't have to know how to calculate the molarity itself from like volumes and grams, for example. That's actually for a later chapter. But just the idea that that's a concentration, it's the amount of substance in a liquid, that's what you need to know. So this is how you write. This is the equilibrium constant, right? So let's say the reaction is this. A, right, in equilibrium with 2B. So let's say it's a type of decomposition reaction, right? Well, how would I write that? Because there's 2B's, right? You actually have to write it twice. In other words, what I'm saying is you have to write like K for this one would be the concentration of B times the concentration of B, like that. And this would be over the concentration of A. So what that means is, though, that B is really raised to the second power. This is B squared over A, like this. So that's really where this number comes from, is because it's basically saying you need 2 molecules in the product to make this reaction happen. And so it's always, this number is always that coefficient is always that number you see up there, okay? A couple of things that are important to recognize, okay, you only include things in the equilibrium constant if they're changing. If the concentration doesn't change, then you don't have to include it. So it turns out there are only two kinds of things that we don't include. One is if it says solid or if it says liquid. These we leave out. Because it turns out pure solids and liquids, their concentrations don't change as you use them. Now, it sounds like that isn't right, but think about it. Will do concentration in grams. Here's a cube, right, of water, and let's say it's 1 centimeter on a side. So this is a 1 centimeter cube, so it's a milliliter cube, right? This would have a mass of 1 gram because the density of water is 1 gram per milliliter. If I use up half the water, well, it's not quite half, but let's pretend I drew it halfway like that. There we go. If I just cut that in half and said, what's the concentration? Well, now it's half a gram and half a milliliter, so this concentration is still 1 gram per milliliter. So it's not going to change in a liquid or solid as you use it up, because as you use it up, its volume changes. Okay, so we don't use those things in equilibrium constants because they don't really help us, it turns out. We just want to look at the things that are changing in concentration. We'll do some more examples down here. Okay, so now one other thing I wanted to point out: if K is really big, it's kind of a relative term. But if you see that phrase, if K is large, what does that mean, right? Well, since K is equal to products over reactants, in order for K to be large, right, at equilibrium, this is describing at equilibrium there would have to be a lot more product than reactant. So we would say if K is large, the reaction favors the product, or is product favored, okay? If K is small, so I'm going to write this product favored. That's simply to say that at equilibrium, there'll be a lot more product than reactant. If K is small, then it's still true that K is products over reactants, but that means for that ratio to be small, the reactants would have to be a lot bigger and numerically than the products, so we would say that it's reactant favored. So in an equilibrium with a small K, you wouldn't expect to see a lot of product.